Why does my machine part have some really weird shapes in those inside corners? Well, I'm going to show you why. Recently, I had an old friend give me a call and ask me some questions about how to set up a CAD model for deep pocketing. He was doing injection molded parts, and he was a really good designer, but he switched companies and they had some different tasks for him to do, and that involved designing machine parts. Part of what he has to do is lightweighting, and some of the lightweighting involved parts that were fairly deep. So there's some concepts that people need to be aware of when you're designing a machine part and you need to do additional steps for lightweighting. So that's what we got into, and that's what I want to show here because it isn't something that a lot of people are aware of, it seems like. Now, as you take a look at this part that I have on screen, you'll note that the bottom pocket of the pocket has some contour, has a little bit of shape. It's doing what it needs to do. And you'll see these really odd shapes in these corners. Okay, you see various steps working their way up. So this obviously has to be cut with a ball, and it's fairly deep. It's a good sized part, but you just can't get in there with a skinny ball that's going to reach all the way to the bottom because you can't have a cutter that's 7, 8, 10 inches long, that's 4, 5, 6, 7 millimeters diameter, and expect to hold any kind of accuracy at the bottom of a very deep pocket. So how do you do it? And there are a couple of things that really should be adhered to. And again, it depends on the machine, depends on who's going to machine it, and depends on various other factors. But I'm talking about, like, let's say this is a 3-axis machine. That's what you're dealing with. And even if it's a 4 or 5-axis machine, you may be able to get a little extra material out of it, but you may be stuck with something very close to what you see on screen. Now, what we have, again, as I mentioned, we have various steps to the machining. Now, if we take a look at the tools, let me come up here and get rid of the subtraction. And let me hide the main body. What you end up having is a tool here that does the subtraction to the lowest with a very large radius. So what you're going to do is you're going to figure out the tool that you need that's going to go to the deepest pocket. Maybe there's some stress issues that you have to have a certain radius size, minimum radius size, but if that's not the case, if you have an 8-inch deep pocket, you're going to have to figure out, oh, can I use a 16 millimeter diameter? Can I use a 10 millimeter diameter? Can I use something, maybe 19, whatever that may be? So you want to figure out what the smallest diameter you can use with a cutter that length that gets into the bottom of the pocket. And that's what this first cutting pass is for. Now, once you've determined that, what you're going to do next is you're going to end up having potentially, again, depending on what it is you need, an additional step or two on the way out because you need to have some light weighting done on the part. So you have an additional machine setup that looks like this, where I have a smaller ball that's coming in, and then I have another machine setup that looks like this, again, another smaller ball. So you're going, depending on the depth of the pocket, 2, maybe 3 additional steps. Highly unlikely you're going 4 unless there's some very specific reason you're doing that. So you end up with the removal of, okay, there's the lowest pocket, there's the next pocket, and then there's the next pocket. Okay, it's common to see this type of thing on parts that have very deep pockets because, again, you need to lightweight, you need to minimize the amount of material, and you don't want to go with too many steps because that could really increase the amount of time it takes to machine the part. Of course, tooling it up and getting things to machine perfectly across these faces is also very tricky. So you want to try to minimize how many steps you take. But again, the amount of material that you remove in areas like this could be pretty profound, could be pretty big based on, of course, what size initial cutter you're using. So obviously if it's a gigantic cutter down here and you're going to step up, you're using much smaller cutters, you're going to remove a significant amount of swarf in that area. All that material is going to be chips on the ground. So that's one very important thing to consider, the length of the cutter. Next is on the vertical corners, you have to have something that's driving around that corner. And I see a lot of people, they just use, if this is, in this case, we take a look at my expressions. I have a ball in here that's 16 millimeters. That's this one down here. So that's a big, gigantic cutter. Again, I'm exaggerating it. And I also have what's called a drive radius. That drive radius is, in this case, 1/2 mil. You may want to add 1 millimeter. And what that does is, as the cutter comes around, it doesn't come to a sharp point right over here. It drives around that corner. Because if it comes to a point, there's a dwell. There's a moment where the machine's cutting in and then changing directions. So there's a potential for an undercut. And if this is a very important part with high stresses and that type of thing, you know that those tiny little chips can lead to big problems later on. So having a driven corner like this, all you're doing is basically adding, again, like you see, 1/2 mil. If I were to come in here and say 1 full millimeter, you're going to see that grow a little bit. These vertical corners grow a little bit. So you want to figure out what the maximum amount, minimum amount, you want to figure out what that is. It could be very small depending on the size of the part, just enough so that the program drives around that corner. It isn't just coming to a stop and then changing directions. So this does not have to be very big. And 1/2 mil, 20 thousandths, sometimes a millimeter, depending on the size of the cutter, is what is necessary. And the same is going to be true for these. Like if I look at the tool for this, so let me come up here, let me hide this body. You'll notice these tools also have that driven parameter around those corners. Okay, the big one, medium one. And this is also going to help with the deep pocketing. Okay, you don't want those sudden stops and changes, as I mentioned, because those sudden stops and changes, again, can impart microscopic little undercuts, potentially chips, something on the surface that leads to potentially a stress riser and other things. So being very thoughtful about what's happening in these scenarios is going to go a very long way. Now, the person that's going to end up programming it, the guy that's going to get this data and program this, when they plot their cutters, they're going to try and get some sort of drive around that corner themselves because they know what could potentially happen. Machines do not like to just stop and suddenly change directions in an instant. Okay, so that is another thing that needs to be considered when you are doing your deep pocketing. Now, this is just good practice in general for any machine part, right? It's just good practice to have that because it's going to make the machinist's life a lot easier. And again, I know it's potentially adding a little bit of material in that corner, but it's better to have a slight bit more material and a part that's not going to fail, because some of those things that could cause a part to fail may not be caught with quality or inspection or anything else. Okay, it does not take much on parts with a high stress load to cause catastrophic failure. It really doesn't. I remember a story I heard years ago, big gigantic train wheels, right? They take these things out and they're forged, and then at some point when they're done machining them, they stamp a serial number on the inner rim of the train wheel. Well, years later, that stamp created a microscopic stress riser, and with all the loads of the train and traveling around, and there's a chunk to chunk to chunk as it travels over those tracks, it caused a massive failure. I don't know how many deaths, and the train obviously derailed and damage and all sorts of other horrible things. And what they had to do is they had to change the process. No more stamping on the inside hub of this big gigantic metallic that looks like it could take a shot from a missile. But again, over time, those things cause problems. So that's why it's important when you're designing your machine parts to try to have that corner. Again, those driving corners are the ones where, if the tool's coming in this case, the Z-direction is coming in, it's plunging in, and it's going to come around. As it comes around, it's going to go around these corners. So think of it as a loop, a racetrack of sorts. Like if you're driving your car around a racetrack, going around a hard corner versus a gentle corner makes a very big difference to the final time. And that's the same thing, same concept is true for your machine parts. So paying attention to at least those kinds of concepts is important. So if you end up with a part that looks kind of weird, like why? That's why. That's for the purposes of deep pocketing. And some people say, well, why don't you just get a 6-axis mill and come in at a very odd angle? Well, maybe you can't. Maybe you don't have the ability to get into that space because the tool holder or whatever can't come in that direction. Or maybe it just adds too much time because now you're doing another setup, coming in at an odd angle, and again, matching this face to make it perfect is going to be very, very difficult. So stuff like that is unrealistic. Truly, it's unrealistic. You really don't want to rely on that. So this type of thing seen in corners is far more realistic. And again, you can shave a fair amount of weight off of a part by doing these various steps. Again, you may have one additional step, you may have 2 additional steps. I don't see really anything greater than that. Again, it's for extreme weight savings, which could potentially be the case for whatever you're working on. So deep pocketing, weird faces, contoured surfaces, ball corners, the works. It's very important you pay attention to the driven corners and just basically all those kinds of concepts when you get into this type of machining. Anyway, hope you learned something. Hope you like what you saw. And of course, subscribe to the channel. That really helps me out. Leave a comment. That helps me out a lot. Like the video. Share with people that you know. And I'll see you again soon.